You know, when you think about getting a medical diagnosis, there is a certain comfort in the precision of it.
Oh, absolutely. It's very visual.
Right. You break your arm, you go to the hospital, they put you in an x-ray machine, and there it is. The doctor points to this jagged white line on a black screen and basically says, there's the problem.
Yeah, it's visible. Categorical, even. You can point a finger at the exact location of the stress.
Exactly. We have this deep psychological need for that kind of visibility, I think. It just makes a chaotic world feel, well, manageable.
When we can physically see the mechanism of failure, we feel like we can control it, or at least fix it.
But then you step into the world of structural engineering, and suddenly that comfort is completely stripped away. I mean, we walk over concrete bridges, we park our cars in these massive multi-story garages.
We stand on cantilevered balconies suspended hundreds of feet in the air.
Yeah, exactly. And we look at these structures as if they are just, I don't know, peaceful, solid, inert blocks of gray stone.
Which is a complete illusion, by the way.
Right. Because the reality that every structural engineer knows intimately is that the inside of that concrete is an absolute violently active war zone.
A war zone is actually a really apt metaphor. The forces at play inside are truly staggering.
It's a landscape of immense, crushing, tearing forces that are completely hidden from the naked eye. And that's exactly what we're getting into today. Welcome to the deep dive.
Glad to be here for this one.
We have an incredibly powerful stack of sources for you today, and our entire mission is to basically give you those X-ray glasses. We are going to make the invisible built environment visible.
And we're pulling from a really fascinating combination of materials for this. We've got rigorous academic calculus breakdowns of force extremes.
The heavy math stuff.
Right, the heavy math.
Yeah.
But also, we're using transcripts from two brilliant engineering educators, Dr. Jod Krushy and the creator behind The Efficient Engineer.
It is a phenomenal synthesis of perspectives, honestly. Yeah. On one hand, you have the unforgiving, mathematically rigid approach of pure calculus.
Which is entirely necessary for the precision required in modern infrastructure, of course.
Sure. But then on the other hand, you have Dr. Krushy's almost philosophical, intuitive approach to visualizing how structures behave before you even touch a calculator.
That's the really fun part.
It is. And what we are going to do with these sources today is completely demystify two of the most intimidating yet absolutely vital concepts in the engineering world.
Shear force diagrams and bending moment diagrams.
Yes. For anyone who follows structural mechanics, you probably know these as SFD and BMD. They are the absolute bedrock of the profession.
You literally cannot build anything safe without them.
So let's set the stakes here for a second. Imagine you have just been handed the blueprints for a massive highway flyover.
Okay, stressful job already.
Right. You are the lead engineer. You are standing on the construction site looking at this enormous expanse of empty air between two concrete pillars.
Just air.
Just air. And you have to absolutely mathematically guarantee that thousands of tons of concrete, steel, and, moving rush hour traffic will not plummet to the ground.
It's a terrifying responsibility when you really think about it.
How do you know exactly where the beam is most likely to snap? How do you know exactly how thick the steel rebar needs to be at, say, exactly 3 meters from the left pillar?
Well, you can't build that flyover on guesswork. And you definitely can't build it by just making the whole thing uniformly thick and heavy.
Because it's too expensive, right?
Economically impossible, and often structurally worse, actually, because you are just adding unnecessary dead weight to the structure.
Oh, wow. Right. More weight means more stress.
Exactly. You have to know the exact internal weather system of that specific beam.
The internal weather system, I like that. And that weather system is mapped entirely by these diagrams?
It is.
So promise to you, the listener, by the end of our conversation today, we are going to break down the mechanics behind these forces so thoroughly that you won't just understand the math.
You'll be able to look at a structure, do a few mental thought experiments, and intuitively visualize exactly how it is trying to break itself apart.
It's going to be like a superpower. Let's start by unpacking this unseen battle inside the beam. The Efficient Engineer notes introduce a scenario that I think grounds this perfectly.
The truck on the bridge.
Yes. Let's say a heavy freight truck parks dead in the center of a bridge span. The beam of the bridge doesn't just passively absorb that weight.
It cannot be passive. I mean, if it were passive, it would yield to gravity and just fall.
Which brings us to the most unyielding law of structural mechanics.
Equilibrium. The universe demands absolute balance.
Right.
If a truck applies a downward force of, say, 100,000 pounds, the bridge And the earth beneath its supports must apply an upward force of exactly 100,000 pounds,
Like down to the exact ounce.
down to the ounce.
Yeah.
If there is even a 1-pound discrepancy, the structure is technically accelerating in the direction of the greater force.
So it's falling or flying.
Basically, yeah.
Yeah. Okay, so the pillars at the ends of the bridge are pushing up, but the truck is in the dead center. There is 50 feet of empty air beneath the truck. How does the immense localized pressure from the truck's tires communicate with the concrete pillars 50 feet away?
The force has to travel.
Right. It's not magic.
No, it travels through the material itself. This is what we mean by internal forces. To maintain that global state of equilibrium we just talked about, the molecules within the steel and concrete must organize themselves to pass that load along.
Like a bucket brigade.
Exactly like a bucket brigade, hand to hand, all the way down to the supports. And the sources distill this complex internal transmission into two primary mechanisms.
Shear force, denoted by the letter V, and bending moment, denoted by the letter M.
Let's visualize these two mechanisms because they behave very differently from each other.
Okay, let's do an analogy. I'm imagining a telephone pole, just a thick, solid cylinder of wood. I've got it lying horizontally across two concrete blocks, one on each end.
Okay, got it.
And then I decide I'm going to drive a bulldozer right onto the middle of it. What is the shear force actually trying to do to that wood?
So imagine the internal fibers of that telephone pole. Shear force is the internal vertical stress of those fibers trying to violently slide past one another.
Like they're rubbing against each other vertically?
Right. If the shear force exceeds the strength of the wood, the pole won't bow or curve. It will cleanly slice in half.
Like a guillotine dropping.
Exactly. The portion of the pole directly under the bulldozer is being forced straight down, while the sections immediately next to it are being held up by the rest of the pole connected to the supports.
Oh, I see.
That intense friction, that vertical sliding action parallel to the cross-section of the wood, that is the shear force.
It's almost like taking a tightly packed deck of cards, gripping the left half of the deck and the right half, and violently shoving your hands in opposite vertical directions.
That's a brilliant mechanical representation.
The immense friction tearing between the two middle cards as they slide past each other, that is shear.
Yes. But shear alone isn't what usually destroys a beam.
Right, because wood bends.
It does.
Yeah.
As you drive that bulldozer onto the telephone pole, the wood is also bowing downward. It's deflecting. And that deflection introduces the second mechanism, the bending moment.
A moment is basically a rotational force, right? Like a torque.
Yes, exactly. When the bulldozer pushes down in the middle and the concrete blocks push up on the ends, those opposing offset forces act like levers.
They are trying to fold the telephone pole into a U shape.
They are. And as the pole bows downward, something critical happens to its geometry. The fibers along the very bottom edge of the pole are forced to stretch out.
Because the bottom of a U shape is longer than the top.
Exactly. They're taking on a longer path. They're being pulled apart. This is what we call tension.
And simultaneously, the fibers running along the top edge directly under the bulldozer treads are being violently squished together into a shorter path.
Right, and that is compression. So that internal rotational effort.
The simultaneous pulling apart of the bottom and crushing together of the top.
Yes, that is the bending moment. And this is so vital because building materials have very distinct personalities.
What do you mean by personalities?
Well, take concrete, for example. It is phenomenal at handling compression. You can squeeze it all day and it holds.
It loves being crushed.
It does. But it is notoriously terrible at handling tension. If you try to stretch concrete, it crumbles and cracks almost immediately.
Which means the engineer's entire job is to track the bending moment, find out exactly where the tension is ripping the concrete apart, and strategically bury steel rebar there.
Because steel is excellent at handling tension.
Right. You put the steel exactly in that location.
Precisely. Without knowing where the shear is trying to slice the beam and where the bending moment is trying to stretch it, reinforcing a structure is just blind guesswork.
Okay, so we know what the internal forces are doing, but before we can calculate them, our sources emphasize that we have to step back and look at the boundaries first.
Yes, the supports.
Right. The foundation of any structural analysis dictates that the way a beam behaves is entirely dependent on how it is held up in the first place.
How you restrain a structure defines exactly how it will fight back.
That makes sense. A beam resting loosely on a brick wall is going to experience entirely different internal stresses than a beam that is deeply bolted and welded into a steel column.
Totally different. And the engineering texts generally categorize these boundary conditions into three idealized types of supports.
The first one, detailed in the notes, is the pin support. Let's unpack the physics of a pin.
Think of a pin support, like a heavy-duty hinge. If you bolt the end of a steel beam to a pillar using a massive steel pin right through a joint, you are locking its position in space.
So it can't move around.
Right, the beam cannot physically move up or down, and it cannot move left or right.
Yeah.
Because the pin arrests that translational movement, it generates reaction forces.
Meaning if you push the beam down, the pin pushes up.
And if you push it left, the pin pushes right.
Okay, I understand the resistance to sliding vertically or horizontally. But what about rotation? If I push down on the middle of that pinned beam, does the pin try to stop it from bending?
This is a crucial distinction. A pin allows free rotation.
Wait, really?
Yes.
Hmm.
Just like a door swings freely on its hinges, the end of the beam is allowed to pivot around the pin as the beam bends under a load.
This actually brings up a concept from Dr. Qureshi's notes that I wanted to challenge, or at least explore a bit deeper.
Okay, let's hear.
He states as a golden rule that a true pinned support transfers shear, meaning it takes the vertical load, but it transfers absolutely zero moment.
That is correct.
But the internal rotational stress right at the pin is zero. At first glance, that feels counterintuitive. I mean, the beam is heavily loaded, it is bending, there's a massive steel joint holding it. Why is there no rotational stress there?
It all comes down to the fundamental definition of stress. Stress can only manifest when there is resistance.
Okay, I'm following.
If you walk up to a solid brick wall and shove it with all your might, your arms will burn with stress because the wall is actively fighting your movement.
It pushes back.
Right. But if you walk up to a freely swinging saloon door and push it, the door simply gives way. You exert energy, but your arms don't experience that intense, crushing resistance.
Oh, I see where you're going with this.
A pin support is the saloon door of rotational mechanics. Because the hinge freely allows the beam to pivot, it offers no rotational resistance at all.
It just lets it bend.
It does not fight the bending motion. And because it doesn't fight back rotationally, no internal bending moment can accumulate at that specific mathematical point.
The pin just happily acts as a pivot, transferring all the rotational stress further down the length of the beam.
Exactly.
I see. It simply refuses to participate in the rotational fight. That makes perfect sense. Okay, what about the second category? The roller support.
A roller support provides even less restraint than a pin. Imagine the end of your beam is resting on a massive, heavy-duty
A
skateboard.
skateboard, okay.
And the skateboard sits on a solid floor. The roller prevents the beam from crashing vertically down through the floor, so it provides a vertical reaction force.
But if you push it sideways...
Right. If you apply a horizontal force, if the beam expands from thermal heat, or if wind pushes it, the skateboard simply rolls. It offers zero horizontal resistance.
And I assume, like the pin, the skateboard allows the beam to freely pivot and curve as it sags.
Yes. A roller allows both horizontal translation and free rotation. It only provides one single vertical reaction force.
It basically says, I will hold you up against gravity, but if you want to slide sideways or bend, you are entirely on your own.
That's a great way to put it.
Which leaves the third and most restrictive boundary condition, the fixed support.
A fixed support is exactly what it sounds like. Imagine taking the end of your beam and casting it deep inside a massive, curing block of concrete.
Oh, wow. Once that concrete sets, the end of the beam is entombed.
It's completely locked. It can't slide vertically, it can't slide horizontally, and there is no hinge. It absolutely cannot rotate.
So because it prevents all forms of translation and all forms of rotation, it generates all three types of reaction.
Exactly. It pushes back vertically, it pushes back horizontally, and crucially, it generates a reaction moment.
A reaction moment, meaning it fights the rotation.
It actively clamps down on the end of the beam, violently resisting the beam's attempt to bow. The concrete wall itself applies a rotational torque in the opposite direction of the bending to force the end of the beam to remain perfectly horizontal.
Man, that is intense. So we have our supports. We know how the structure is anchored. The next logical step is to look at what is actually attacking it.
The loads.
Yes, the loads. And the engineering texts don't just use a generic term like load. They categorize external pressures into highly specific mathematical models.
They have to, because a sudden, sharp impact behaves very differently than a slow, spreading accumulation of weight. The notes detail 3 primary loading scenarios that an engineer will map onto their blueprints.
The first one is probably the most intuitive. The point load, sometimes called a concentrated load.
Right. A point load assumes that a massive amount of force is being channeled into one mathematically infinitely small location on the beam.
Of course, in reality, nothing is infinitely small.
No, but if you have a heavy steel column resting on top of a wide horizontal beam, the area of contact is so small relative to the entire structure that engineers just treat it as a single point of pressure.
The analogy often used is a person standing completely still on one foot on a wooden plank. All of their body weight is driving down through the tiny surface area of their heel.
Exactly. On an engineering diagram, this is drawn as a single, harsh, localized arrow pointing straight down.
And it creates an aggressive, localized spike in shear force right at that location.
It does. The second scenario is the uniformly distributed load, or the UDL.
This is what I like to call the snow on the roof scenario.
Yes, that's perfect. Instead of a single column resting on the beam, imagine a thick, dense slab of reinforced concrete lying perfectly flat across the entire length of the beam.
So every single inch of the beam is supporting the exact same amount of weight.
Correct. If you walk 1 meter down the beam, you're carrying, say, 10 units of weight. If you walk another meter, you're carrying another 10 units. It spreads out.
In the math, how is this usually represented?
It is measured in terms of intensity over distance, like kilonewtons per meter.
Okay, what's a kilonewton, practically speaking?
A kilonewton is roughly the weight of a heavy adult man. So a load of 10 kilonewtons per meter means every single meter of the beam is supporting the weight of 10 men.
Wow. And on a diagram, it looks like a continuous rectangle of tiny downward arrows covering the whole span.
Exactly. And the third type is where it gets a bit more complex. The uniformly varying load, or UVL.
Varying load, so it doesn't remain constant.
Right. It increases or decreases at a steady, predictable rate along the beam. Instead of a rectangular block of weight, it forms a triangular wedge.
What is a physical reality that would actually cause a triangular load?
The classic example is hydrostatic pressure. Think of water pushing against a retaining wall or a dam.
Oh, like a swimming pool.
Yeah. If you dive into a pool right at the surface, the water pressure against your ears is essentially zero. But as you swim deeper and deeper, the sheer volume of water stacked above you increases linearly.
Oh, I see. So at the very bottom of the Hoover Dam, the horizontal pressure pushing against the concrete is monumental, whereas at the top lip, it is minimal.
Exactly. The load varies uniformly from 0 to maximum.
Okay, so we've established the anchoring, and we've established the attacks, the point loads, the UDLs, the UVLs. The efficient engineer transcript states that the first operational step of any analysis is to establish global equilibrium.
Before you can ever hope to understand the internal shear or bending moment, you must balance the books externally.
Right.
You have to know exactly how hard the supports are pushing back.
And we do this using the basic equations of classical mechanics. The sum of all vertical forces equals 0, and the sum of all moments around any pivot point equals 0. We literally just balance the downward arrows with the upward arrows.
Yes, it's basic accounting,
Yeah.
structurally speaking.
Now, I want to clarify something here for you, the listener. The sources briefly touch upon structures that are statically indeterminate.
Ah,
These are structures with so many fixed supports and complex anchors that the basic equations of equilibrium simply aren't enough to solve for all the unknown reactions. You end up with like 4 variables and only 2 equations. The math breaks down.
well, the mass of statics breaks down, yes. Statically indeterminate structures are highly redundant, they're incredibly safe, but they are analytically very complex.
So how do you solve them?
To solve them, you have to abandon simple equilibrium and start calculating exactly how much the physical material itself will microscopically stretch and compress. You have to enter the realm of material elasticity and compatibility equations.
Which is fascinating, but the efficient engineer makes a strategic pedagogical choice here, and it's one we are going to follow for this deep dive.
We're going to focus entirely on statically determinate structures.
Right. Not because indeterminate structures are an annoying headache to be avoided, but because the foundational truth of how shear and moment interact is universal.
Exactly. If you can master the internal mechanics of a simple determinate beam, that exact same physical logic applies to the most complex suspension bridge in the world.
We are isolating the variables to understand the pure mechanism.
Exactly.
So, assuming we have balanced the global books, we know the truck pushes down with 100 kips and the left support pushes up with 40 and the right support pushes up with 60. We know the outside.
Right.
But what is preventing the concrete in the dead center of the bridge from just ripping apart? Knowing the reaction of a pillar 50 feet away doesn't tell me what the concrete is feeling right under the truck's tires.
I should look inside.
How do engineers mathematically pry open a solid steel beam?
They use a conceptual tool that is the undisputed core of structural analysis. The method of sections, or colloquially known as the cut method,
The cut method.
it is a profound thought experiment. To find the internal forces, you mentally destroy the beam.
You literally slice it in half.
Yes, but let's use an analogy that really captures the physics. Imagine two people are engaged in a fierce game of tug-of-war.
Okay, pulling rope.
They're pulling on opposite ends of a thick rope with incredible force. They are at a standstill. Equilibrium. The rope is perfectly still, but it is incredibly taut.
Right.
Now, I ask you, exactly how much tension is inside the exact center of that rope? You can't put a scale on the outside of the rope to measure it.
Right, because it's completely hidden inside the fibers.
The only way to find out is to take a machete and slice the rope exactly in half.
But wait, if I cut the rope, the two people fall over backwards, the equilibrium is completely destroyed.
Exactly, the system fails. Unless the very microsecond you cut the rope, you grab the newly severed end of the left half and you pull on it yourself.
Oh.
If you pull with the exact same amount of force that the right side person was originally pulling with, the left side person will stay perfectly still. They won't fall over.
You have restored equilibrium.
You restored it.
That is brilliant. So by stepping in and manually holding the severed rope, I have effectively replaced the internal force of the rope fibers with my own external measurable force. I can literally feel the tension the rope was experiencing.
That is the cut method, in a nutshell. You make an imaginary slice down a beam at any specific coordinate, say exactly 5 meters from the left support. You take the entire right side of the bridge, and you throw it into the ocean. It's gone.
Just mental deletion.
Right. And because the original whole bridge was in perfect equilibrium, this newly severed left portion must also be kept in equilibrium. It cannot be allowed to plummet to the ground or start spinning wildly in the air.
So at the exact face of the cut, the internal material of the beam was acting like the glue holding the universe together.
It was. It was providing an internal vertical shear force to stop the left side from falling and an internal rotational bending moment to stop it from spinning.
Wow. So by making the cut, those hidden internal stresses are suddenly exposed. They become mathematically treated as external forces acting on our severed left piece.
Precisely. And because that piece must remain stable, those newly exposed internal forces must mathematically cancel out all the other external loads acting on that left piece.
Let me make sure I've got this math right. If I have a 100 kilonewton pillar pushing up on the far left and a 20 kilonewton truck pushing down on the span, at my cut face, the internal shear force simply must be 80 kilonewtons pushing down to balance the vertical map.
That's right. 100 up minus 20 down minus 80 down equals 0.
It's just simple bookkeeping.
It is elegant, irrefutable bookkeeping. You slide your imaginary cut down the length of the beam, millimeter by millimeter, continuously recalculating that balance and plotting the internal values on a graph.
And that graph becomes your shear force diagram.
Exactly.
But, and this is a massive warning light flashing in the sources, if you are going to use this cut method, you must be religiously obedient to a diagnostic sign convention.
Oh, absolutely. A strict convention is the only thing preventing structural catastrophe.
How so?
Well, if an engineer calculates a value of, say, 50 kilonewtons of bending moment, that number is completely useless and incredibly dangerous if they don't know whether that moment is bending the beam upwards or downwards.
Because you need to know where the tension is.
Right. If you confuse positive for negative, you put the tensile steel reinforcement on the wrong face of the concrete, and the beam will violently snap under its first live load.
Okay, let's clearly define the convention used globally. Let's start with shear force. When I make a cut, how do I know if the shear is positive or negative?
Imagine your severed beam again. You have the left piece in one hand and the right piece in the other.
Okay.
Shear force is universally defined as positive if the internal force on the face of the left piece is pushing UP and the internal face of the right piece is pushing down.
Left piece goes UP, right piece goes down. It's almost like a clockwise sliding motion.
Correct. Therefore, if the force is reverse, if the left piece is being forced down and the right piece is being forced UP, creating a counterclockwise shear, that is marked as negative on your diagram.
It requires strict discipline to track, but it's very logical. Now, what about the bending moment sign convention? Because the sources say this one is fundamentally crucial for visualizing the physical distress of the material. This is the concept of smiling versus frowning.
Yes, the smile and the frown. A positive bending moment is technically referred to as sagging. Imagine holding a long, flexible plastic ruler between your hands and you push down in the dead center. The ruler sags. It bows downward into a U shape.
It literally curves into a smile.
Yes. And structurally, what is happening during a positive sagging smile, the material at the very bottom edge of the ruler is being stretched. The tension is at the bottom. The material at the top edge is being compressed together.
So smile equals sagging equals tension on the bottom.
Exactly. And conversely, a negative bending moment is called hogging. This occurs when a beam is forced to droop over a support.
Like a diving board.
Yes. Imagine a diving board extending out over a pool. When a swimmer stands on the end, the board bends downward over the fulcrum. It bows into an upside-down U shape.
Which looks exactly like a frown.
And in a frowning, hogging beam, the physics completely invert. The top surface of the diving board is the part being violently stretched apart as it droops. The tension has moved to the top.
And the bottom surface is being compressed against the support.
Right.
So frown equals hogging equals tension on the top. So this convention isn't just about drawing pretty graphs above or below an axis line on paper.
Not at all.
It is a direct physical map telling the construction crew, hey, the graph is positive here, so wire the heavy steel rebar along the bottom of the concrete formwork. The graph dips negative here, so move the steel to the top.
It is the architectural DNA of the beam.
Okay, we are building a really solid foundation here. We understand the equilibrium, we understand the cut method, and we have our smiling and frowning conventions to track exactly where the tension lives.
Which is the ultimate goal.
But I have a practical, logistical problem with this.
Go ahead.
If I am an engineer designing a continuous viaduct that is, let's say, 2 miles long, taking an imaginary machete and calculating the equilibrium of thousands of individual slices, millimeter by millimeter, sounds like a medieval torture method.
It sounds awful.
It is incredibly tedious, it's prone to arithmetic errors, and it just seems entirely inefficient.
It is, which is why the cut method, while conceptually essential to understand what internal forces actually are, is rarely used for complex continuous analysis in practice.
There's a better way.
The universe is much more elegant than that. There is a deep underlying mathematical symmetry in structural mechanics.
This brings us to what I like to call the mathematical cheat codes. The calculus linking the external world to the internal world.
We don't need to slice the beam 1,000 times because the external load, the internal shear, and the internal moment are not independent phenomena. They are the exact same physical energy, just accumulating in different dimensions.
And the language of accumulation and rate of change is calculus. Let's break down the two master equations from the academic notes. Equation 1 links the external load to the internal shear force. The equation is basically dV over dx equals negative W.
Now, let's try to avoid just reading algebraic formulas aloud. What is the physical truth of dV over dx?
Right. In graphical terms, a derivative is simply the slope or the steepness of a line.
Yes. So this equation tells us that the steepness of the shear force diagram at any given inch along the beam is exactly dictated by the intensity of the external load, pushing down on that exact inch.
Let me make sure I'm picturing this right. If I have a massive, heavy concrete slab, a uniformly distributed load, pushing down across a section of the beam, the load intensity is constant. It's a flat, heavy pressure.
Because the load is constant, the equation dictates that the slope of your shear diagram must also be constant.
And a line with a constant slope is just a straight, angled ramp.
Exactly. So under a uniform load, your shear force graph will simply be a straight line sloping cleanly downwards. The external weight is literally dragging the internal shear down at a constant rate.
The load acts as the steering wheel for the shear. That is incredibly direct.
It's a beautiful relationship.
And then we have equation 2, which links the shear force to the bending moment. The equation is dm over dx equals v.
Applying the exact same philosophy. The slope, or the steepness, of the bending moment diagram is perfectly equal to the actual numerical value of the shear force at that specific location.
Wait, so if my shear force is a massive positive number, say right next to a heavy support pillar, my bending moment diagram is going to be angled upwards incredibly steeply.
It's climbing a shear cliff.
And as the shear force gets smaller, the bending moment graph starts to flatten out.
Yes. The shear force dictates the trajectory of the bending moment.
This logic leads to one of the most critical concepts in all of structural engineering. It's basically the ultimate aha mechanism for finding structural danger.
The zero shear point.
Yes. What happens at the exact mathematical point where the shear force equals 0?
This requires us to think about the philosophy of calculus, specifically the calculus of extremes. Think about the trajectory of a thrown baseball, or, well, a roller coaster cresting a massive hill.
Okay, picture the roller coaster.
When the roller coaster is climbing, its slope is positive. It is gaining height. When it drops down the other side, its slope is negative. It is losing height.
Right.
But what happens at the absolute microscopic apex of the hill, just for a fraction of a millisecond between the climbing and the falling, the roller coaster is completely flat. Its slope is exactly zero.
It has stopped increasing but hasn't yet begun to decrease.
Exactly. In mathematics, when the derivative or the slope of a curve hits zero, it is a flashing beacon telling you that the underlying function has just reached its absolute local maximum or local minimum.
It has hit the peak of the mountain or the bottom of the valley.
Now, apply equation 2 to this logic. We established that the shear force is the slope of the bending moment.
Oh, I see the radar sweeping. If the shear force graph crosses the zero axis, like if it goes from positive to negative, that means the slope of the bending moment has just hit zero.
Which guarantees, with absolute mathematical certainty, that the internal bending moment has just reached its highest possible peak, its maximum extreme.
The moment accumulation has crested the hill.
Yes. You don't have to guess where the beam is experiencing the most violent tension. You don't have to make 100 cuts and compare the values.
You simply draw the shear force diagram, look for the exact spot where the line crosses zero, and you basically draw a big red X on your blueprint.
That is your danger zone. That is where the beam is most likely to snap. That is where you concentrate your heaviest steel reinforcement.
Calculus acting as a structural radar, that is profoundly elegant. But practically speaking, if an engineer is in the field looking over schematics on a drafting table, taking algebraic derivatives and integrating polynomial equations isn't exactly a fast visual process.
No, it's not.
Is there a way to harness the power of this calculus without getting bogged down in the algebra?
Absolutely. The Efficient Engineer transcript highlights the method that engineers actually use on paper. It's called the area method. It relies on the inverse of the derivative, which is the integral.
And in visual terms, taking an integral simply means calculating the geometric area underneath a graph.
Exactly. So how does calculating area replace calculating equations? It allows you to build the diagram sequentially, just by finding the area of simple shapes.
Let's hear the rules.
Well, number one, the change in shear force between any 2 points on a beam is simply the total geometric area of the external load resting between those 2 points.
Wait, let me test that. Let's go back to our uniformly distributed load, a flat slab of concrete. Let's say it weighs 10 kilonewtons per meter, and it covers exactly 5 meters of the beam. On a diagram, that load is just a rectangle.
Right, a rectangle with a height of 10 and a length of 5.
The area of a rectangle is base times height, so 5 times 10 is 50. Are you telling me that without any complex equations, I know for a fact that my internal shear force drops by exactly 50 kilonewtons over that span?
It's exactly 50. You start at the known shear value from your support reaction, and you simply subtract the area of the load rectangle. You just plot your next point 50 units lower.
Feels almost like a cheat code.
It does, doesn't it? And it compounds. Rule number 2. The change in bending moment between any 2 points is the total geometric area under the shear force diagram.
So I use the area of the loads to draw my shear graph. Then I look at the shapes I just drew on my shear graph, which are usually just triangles and rectangles, and I calculate their areas.
Yes.
And those basic half base times height calculations tell me exactly how high my bending moment graph climbs.
Yes. If your shear diagram creates a triangle with a base of 4 meters and a height of 20 kilonewtons, the area is 40. Your bending moment increases by exactly 40 kilonewton meters. You build the entire structural analysis using the geometry of a middle school math class.
The sources outline a pattern that naturally emerges from this area method, which they call the escalating geometry of beam responses. The texts frame it almost as a memorization tool, like flat goes to sloped, sloped goes to curved, but I really want to understand why the physical world requires this escalation. Why do the shapes change?
The physical world requires this escalation because we are witnessing the cascading accumulation of forces over a distance. Let's look at the physics of it.
Okay.
Imagine you are pushing a heavy sled across a frozen lake. If you apply a constant pushing force, your speed doesn't stay constant. Your speed accumulates. You accelerate. You move faster and faster.
Right. My constant force escalated into a sloped increasing velocity.
And as your velocity increases, the distance you cover doesn't just increase steadily. It increases exponentially.
Yeah.
You cover vastly more ground in the 10th second than you did in the first second.
Exactly.
That is the physical reality of integration. It is compound interest. Now let's apply that cascading accumulation to a beam.
Scenario 1. A constant, uniformly distributed load. A flat, heavy block of concrete. A 0-degree polynomial, a horizontal line.
Because every single inch of the beam is feeling a constant weight, the internal shear force has to accumulate that weight inch by inch.
Yes. So the shear force escalates to become a 1st-degree polynomial, a linear slope. It ramps downward steadily.
Because the load was flat, the shear is sloped. And now the bending moment has to accumulate that slope shear.
Exactly. The shear is getting larger and larger as it ramps down. So the bending moment isn't just accumulating at a steady rate, it is accumulating at an accelerating rate.
The compound interest kicks in.
And geometrically, an accelerating accumulation forms a 2nd-degree polynomial, a parabola, a smooth, sweeping curve.
Flat load escalates to slope shear, which escalates to parabolic moment.
And if we step it up one more level, Scenario 2, the uniformly varying load. The triangular water pressure pushing against the dam, the external load itself is already sloped. It's a linear variation.
So the accumulation starts one step higher. The sloped load escalates the shear force into a parabola.
And the parabolic shear escalates the bending moment into a 3rd-degree polynomial, a cubic curve, a complex, swooping S-shape of accumulation.
By understanding this physical reality of compounding accumulation, combined with the area method, an engineer can essentially sketch out an incredibly accurate, visually proportional map of the internal forces just by glancing at the shapes of the loads.
Which perfectly sets the stage for the final and honestly most profound level of structural mastery discussed in our sources.
Yes, this is where we transcend the numbers entirely.
This is the focus of Dr. Jod Qureshi's incredible lecture series. He basically states that while grinding through the area method and the calculus is academically necessary, the true mark of a master engineer, what he calls level 1 structural behavior, is the ability to draw these bending moment diagrams purely by intuitive physical inspection.
No calculators,
Yeah.
no given load values, no dimensions, just looking at a skeletal structure and instantly seeing how it wants to contort itself.
It sounds almost like a parlor trick, or intuition bordering on magic. How do we bypass all the math we literally just spent the last half hour establishing?
Well, it isn't magic. It is a rigorous application of physical empathy. Dr. Qureshi lays out a strict 3-step intuitive method. You must discipline your mind to follow these steps sequentially.
Step 1. Identify the points of certainty.
Anchor points.
Exactly. Before you try to imagine the whole beam bending, you need to lock down the points that mathematically cannot move. Look at your supports. If you have a pin support on the left, you know absolutely that the deflected shape of the beam must physically pass through that exact coordinate.
It cannot float above it. It cannot sink below it. It is locked.
And as we established earlier, because a pin allows free rotation, it cannot fight the bending moment. So we know the bending moment diagram must equal exactly 0 at that pin. It must cross the 0 axis. That is a point of certainty.
Correct. You establish your anchors. Step 2. Sketch the deflected shape and find reaction directions.
This is where the physical empathy comes in. Qureshi asks the student to imagine the solid steel beam is actually made of highly elastic, soft rubber.
Yes. Look at where the heavy load is positioned and visualize how that rubber would wildly squish, stretch, and deform under the pressure. Sketch that exaggerated drooping shape.
But here is where the intuition reaches its peak.
Yeah.
How do we figure out which way the supports are pushing back without doing our equilibrium equations?
Dr. Qureshi shares a brilliantly simple mental shortcut for this. The support removal thought experiment.
Support move.
To figure out the hidden purpose of a support, you mentally delete it from existence. Erase the pillar from the blueprint. Now look back at your rubber beam. Without that pillar holding it, what does the heavy load do to the beam?
Without the restraint, the beam is going to wildly deflect. It might crash catastrophically downwards to the floor, or if it's overhanging another support, the far end might flip violently up into the air like a seesaw.
Now, in your mind's eye, put the support back. The required reaction force of that support is simply the force needed to grab that wildly flailing beam and forcefully push or pull it back to its original locked position.
That is so intuitive. If I remove a pillar and the bridge span collapses downwards, then the pillar's entire purpose in life must have been pushing UP to prevent that collapse.
Right.
If I remove an anchor bolt and the tail end of a cantilever flips up into the sky, then that anchor bolt's entire job must have been violently pulling down to restrain it.
You have deduced the exact direction of the reaction forces simply by observing the tendency of the deformation. No equations required.
Which leads to step 3. Draw the bending moment diagram on the tension side.
Because you have already sketched the exaggerated rubbery deflected shape, you can physically see where the beam is sagging into a smile and where it is hogging into a frown. You can literally see where the fibers are stretching.
Dr. Kershey's rule of thumb for intuition is to draw the blocks of your diagram on the side of the beam, experiencing that tensile stretching.
If it's a sagging smile, the bottom is stretching, so you draw the bending moment peak below the axis line. If it's a hogging frown, the top is stretching, so you draw the peak above the line.
Let's put this three-step intuitive method to the absolute test. Let's walk through two highly practical, complex structural examples taken directly from Dr. Kershey's advanced lectures. I really want you, the listener, to try and visualize the physical forces here.
Okay, let's do example 1, the back-to-back cantilever.
Picture a long, continuous beam. It is supported by three pillars, one on the far left end, one on the far right end, and a heavy column acting as a prop right in the dead center.
Okay, left, center, right. Got it.
Now, sitting perfectly, exactly balanced on top of that middle center prop is a massive, incredibly heavy point load, say an industrial steel boulder.
So we have a beam, 3 supports, and a boulder resting directly above the middle support. How do we draw the bending moment purely by intuition?
Follow the steps. Step 1. Points of certainty. The beam must pass through all three supports. The bending moment at the outer pins is 0.
Step 2. Deflected shape and reactions. Let's look at that load. The boulder is massive, but it is sitting directly, plumb line straight, on top of the solid middle column.
The column is taking the brunt of it. The boulder pushes down with immense force, and the column pushes back up with the exact same immense force.
The structural threat is entirely neutralized right there in the center. The load goes straight into the earth. So if the load is completely absorbed by the middle prop, what do the supports on the far left and far right ends feel from that boulder?
If the middle is doing all the work, the ends feel nothing. They are just bystanders.
Precisely. The outer reactions effectively become 0 in relation to the point load. Now let's look at the beam itself. Even though the boulder's weight is neutralized, the beam has its own self-weight. It's a heavy piece of steel spanning across empty air on either side of the middle prop.
Right. The left span and the right span are still subject to gravity. So how does our rubber beam deflect? It's pinned rigidly in the dead center by the massive weight of the boulder pushing down on the prop. But the outer spans aren't being actively held up by any significant fighting force because their reactions drop to 0.
I can see it. If it's pinned in the middle and the ends are just floating there under their own weight, both ends are just going to lazily sag downwards. It looks like a wet noodle draped over a fork, or like a seagull with its wings dripping down.
Yes, the beam droops downward symmetrically on both sides of the center prop. Structurally, it behaves exactly like two separate diving boards placed back to back. They are fixed in the center and drooping freely on the ends.
And if both ends are drooping downwards from a central peak, the entire structure is forming one massive continuous frown over the middle prop.
A frown, which means what kind of internal bending moment?
Hogging, negative moment. The droop is stretching the fibers across the entire top surface of the beam, peaking right over that middle prop. And there is your diagram. Without a single mathematical equation, you know that the bending moment diagram is a massive negative triangle. The peak of the triangle, the point of maximum danger, is directly over the middle prop, representing pure hogging tension. The diagram slopes back down to 0 at the outer ends. You saw the physics, and the diagram practically drew itself.
That is incredibly satisfying to deduce. Let's try the second example, because this one introduces a really tricky nuance of proportional logic.
Example 2, the double overhang beam.
Picture a continuous beam, but this time the two supports are relatively close together in the middle. The beam overhangs significantly on the left side, past the support, and it overhangs significantly on the right side.
It looks like a seesaw, but with 2 fulcrums spaced out in the middle instead of just one central pivot.
Right. Now imagine we apply 2 point loads. We grab the extreme left overhanging tip and we pull it violently straight down. Simultaneously, we grab the extreme right overhanging tip and we pull it straight down.
Okay, pulling both tips down, let's run the intuition. Step 1, points of certainty. The beam must remain attached to the 2 middle fulcrums. The moment at the very free ends is 0.
Step 2, deflected shape. If I pull the outer tips down, they are going to bend downward. But because the beam is rigid and pinned at the 2 fulcrums, pulling the ends down acts like levers, it violently forces the middle span, the section between the 2 supports, to bow upwards into the air.
Picture the rubber beam conforming to that. The 2 ends droop down and the middle aggressively arches up.
So the entire continuous length of the beam, from the left tip to the right tip, is shaped like one giant undulating frown.
Yes. The entire top surface of the beam is being stretched. It is experiencing 100% negative hogging moment across its entire length. There is no sagging anywhere.
But here's where Dr. Qureshi tests the master student. You know it's all negative hogging. But which part of the beam is experiencing the most extreme tension? Is the peak danger over the supports where you are pulling down? Or is the peak danger in the middle span that is arching high up into the air?
Visually, my initial instinct says the middle span. Because it's arching so high upwards, it feels like the stretch at the apex of that arch would be the most severe.
It is a very common intuitive trap. To break the trap, we apply a tiny bit of proportional logic based on the underlying mechanics. Let's look at the leverage.
The rotational moment at the overhanging ends is generated by the load at the very tip, multiplied by the full length of the overhang arm. If the load is W and the length is L, the moment is roughly proportional to W times L squared.
A massive lever arm creating a massive torque at the fulcrum.
Exactly. Now look at the middle span. The moment there isn't being driven by a direct load pushing down on it, it's merely a reactive arch caused by the leverage at the ends. The mathematical distribution between two supports generally yields a proportional moment of W times L squared divided by 2.
Oh, I see the math. The rotational force grinding into the fulcrums is a full WL squared, but the reactive arch in the middle is only half of that, WL squared over 2. Mathematically, the torque at the supports is vastly larger.
Exponentially larger. So when you visualize the diagram on the tension side, you draw massive, sharp, jagged peaks of negative hogging moment directly over the two supports. And connecting those two massive peaks is a much shallower, swooping curve representing the middle span. The stress peaks at the supports dramatically dwarf the arch in the middle.
You visualize the rubbery deformation, you sense check it with proportional leverage logic, and you map the exact points of failure. The concrete over those two supports better be packed solid with heavy steel rebar along the top edge, or the whole overhang snaps off.
It is a superpower. You are seeing the invisible forces dictate the physical reality of the structure.
Okay, let's take a breath and recap this incredible journey. We started by shedding our assumptions about peaceful, solid buildings and defined the violently active, unseen battle inside every structure. The sliding, shearing friction of vertical forces, and the rotational, stretching torque of bending moments.
We established that boundaries dictate behavior. We analyze how a structure fights back against gravity through pin pivots, sliding rollers, and rigid, fully encased fixed supports.
We mapped out the real-world attacks, the localized point loads, the heavy distributed slabs, the varying hydrostatic water pressures, and we used the unyielding laws of global equilibrium to balance the external books.
Then we took our imaginary machete. We used the cut method to expose the internal stresses, establishing the strict boundary of our sign convention. Positive shear, meaning a clockwise slide, and positive moment, meaning a sagging, smiling beam with tension violently stretching its bottom fibers.
We unleashed the mathematical radar. We proved through the elegance of calculus that the internal shear force is nothing more than the physical slope of the bending moment, and crucially, that the exact moment the shear hits zero when the accumulation stops, we have pinpointed the absolute maximum peak of structural danger. We bypassed the algebraic equations entirely using the area method, physically stacking the geometric areas of rectangles and triangles to map the cascading escalation of forces.
And finally, we transcended the math entirely. We adopted Dr. Qureshi's intuitive physical empathy, mentally deleting supports to watch rubber beams wildly contort, allowing us to accurately map the hogging and sagging tension zones without ever picking up a calculator.
It is a profound, complete toolkit for understanding the hidden bones of the built world around us. And I want to underline why this matters to you, the listener. The next time you walk across a massive, wide-open floor in an airport terminal, or you drive your car over a long, sweeping concrete bridge spanning a river, you aren't just trusting that the concrete looks thick enough. You are trusting the meticulous, uncompromising calculation of these exact shear and bending diagrams.
The invisible forces we spent the last hour discussing are constantly flowing around you right beneath your feet. An engineer sat down with a blueprint, visualized the double overhangs and the uniform loads, found the zero shear point, mathematically mapped the exact millimeter of highest tensile stretch, and buried the steel exactly where it needed to be to keep you safe.
It is the silent, ongoing triumph of applied physics. It truly is. But before we sign off, I want to leave you with one final provocative thought, a thought experiment to mull over the next time you look at a skyline.
I'm ready for this.
Throughout this entire deep dive, we have based our intuition and our calculus on a fundamental assumption that the beam is made of a rigid, static, uniform material. Concrete, steel, wood, materials that are forged in a specific shape and then just sit there passively taking whatever stress the universe throws at them.
Right, classical materials.
But engineering is evolving. What happens to our structural intuition if the material is no longer uniform or passive? What happens to the shear force and bending moment diagrams if a bridge is built out of a smart, adaptive metamaterial? Imagine a beam that is laced with sensors and actuators capable of dynamically changing its own stiffness in milliseconds. A material that purposefully becomes rigidly stiff exactly where it senses incoming tension and relaxes into flexibility where it senses compression, actively rippling and reacting as a heavy freight truck drives across the span.
Wow, that completely shatters the classical models. How does the calculus equation, where shear is the derivative of moment, hold up when the underlying physical elasticity of the material is constantly dynamically rewriting its own rules second by second to outsmart the load?
Exactly. Does the danger zone of zero shear even exist if the material instantly disperses the stress? We have spent today mastering the static, classical beam, but the dynamic, artificially intelligent structure, that is a deep dive for another day. Thanks for joining us, and we'll catch you on the next one.